Okay, I'm going to go over a LabVIEW VI that we've written, a timed table-driven feed VI, that's designed to provide reloadable table-driven feed control for a benchtop sartorius fermentation system. The system has 4 channels, basically because our sartorius system has 4 channels, and it's a LabVIEW VI. I'm not going to go through LabVIEW VI's, well, the basics in detail, because there's some great tutorials online from National Instruments that give a really good background in an introduction to the LabVIEW development environment. I will go over a few things that are pertinent to this particular VI. Now, a LabVIEW VI always consists of 2 things. It has a front panel, and it has a block diagram. The front panel is the user interface, and the block diagram is where the logic is defined. Now, right here, we're looking at the front panel of the VI in question. And what it has is it has a bunch of setup information here. These are controls, meaning you enter information here that then is used to control the VI. And it has readbacks here where it gives you the status of each channel, and also gives you some control over manual overrides. So the first thing I'm going to do is I'm going to turn on context help. And what this does is it essentially, if you hover over things, it will display things that the system knows about the various items. So we have a text entry for our location for our communication DLL. We have our time base here, and it's talking, and notice what it does is it says the name of the unit and the representation of the unit, and then gives a little graphic. Now there are also compound controls, and this channel control is an instance of this. What it is, we can see over here, is it's an array. It's an array of channel clusters. Now clusters basically are user-defined data types where you basically can assemble a bunch of variables that have a related purpose. It basically makes life a little easier as far as wiring the diagram, and you'll see this as the video goes on. And there are 4 instances here, and so what it shows you here is that yes, there's a 1D array of a channel, and each of these channels has 8 elements. And once again, you can see the names here, a little graphic, and then a description of the data type that it's involved with. The same thing is true for the displays here. We have our current data. This is the status for each channel. And again, it's a 1D array of a cluster, which is a collection here of the various data items that are of interest to each particular channel. The last one here is a manual feed override. And again, this is a much simpler one, but it's also an array of clusters, and each cluster just contains a run and a stop button. This guy over here is the global feed enable control. So with this done, we will now transition over to the block diagram. Now, LabVIEW block diagrams are obviously graphical depictions of logic. They generally execute from left to right. And again, the context help is useful because we can hover over various things. Now this, of course, is where the elapsed, I guess I should move this over so it's easier to see in one place. The elapsed time units, this is what's setting the time base. This is a constant that is of type, of our current data type. This is the data status. Here, of course, is our DLL location. Now let me go over a few of the, obviously we can go over the various controls, and up will pop all the descriptions of the channels and all the items that are included in them. So now let's move on quickly to some of the program elements here. I'll change this to a selection. Now, the way this VI works is that there's basically there's a loop that runs forever until it's stopped by the user. This outside loop here, or this outside box, is a, let's see if we can get something to come up, is a timed loop. And the timed loop basically executes everything that's within it at a particular rate. The rate is given by the elapsed time units and the clock here. And so in our case, we generally send the elapsed time units to 1,000 milliseconds. We count down with a 1 kilohertz clock, and what this does is it ensures that everything inside here is executed once per second. One of the interesting things about the way LabVIEW executes is that before it executes this external time, this timed loop, it will basically read in the values here that are outside of it, that are connected to it. And then once execution continues to the loop itself, what happens is they're never read again, because they're only read when the execution path follows them. So they're read once at startup, and then forever they can't be changed after that. Now these controls here that are inside the timed loop, these are basically reread every time the loop executes. And once again, the execution is from left to right. So what it's doing is every second, it's going to read the channel control, the manual feed override, and the global enable control. And then these are arrays of 4. Well, the global enable is not. But then it proceeds to an inner for loop. And a for loop, you can tell a for loop, it has a little N in the upper left-hand corner, looks like a stack of papers. Generally, there's a constant connected to N, which means it will execute a fixed number of times. So if you had 4, for instance, it would execute 4 times. Now, LabVIEW, of course, has some tricks involved. And so in LabVIEW, if you wire an array type to a for loop, and you use the default kind of little tunnel here, what will happen is that it will say, aha, what we're going to do is we're going to execute the for loop for once per element in each connected array. Now, of course, what we have here is we have 2 arrays that are that are made up of 4 elements, so there's no confusion for LabVIEW as far as how many times to execute. If these were different size arrays, then one would have to add something explicitly to the iteration count to ensure that it would not be ambiguous. One of the things we'll see right away here is that now channels, of course, yes, so that's where the channels are. Let me put this back here. If I hover over channels, this is the description. Just like on the front panel, it displays the entire the data type. And what we can do here is we can actually peel off, we can unbundle from the cluster by name, because the array of clusters goes through the for loop and now becomes a single cluster because it's working 1 element at a time. And then we can pull off by name, and you can see the channel enable is in here somewhere. Channel enable right here. The idea is that you can pull things off the cluster, and one thing you can see right off is how the cluster simplifies some of the wiring here. And so what happens here is that the data comes through these so-called wires, through these so-called connectors, and basically now we went from an array to individual elements, and now that we have an element, we can take the pieces of that element and deal with them. Well, the first thing that we do here is we're going to go into yet another loop. Now, let me stop for just a moment and clarify that of what I'm not going to go over in this video. I'm not going to go over the detailed functionality of the VI. I'm just really going to go over the data structures and the programmatic elements so that we get an idea as to what the logic, what these elements do. So we immediately go into yet another functional block here, and this is a case statement. This case statement, there's a selector here that's connected to a Boolean, And essentially what's happening here is you're taking the Boolean AND of the channel enable and the global enable, and if the channel is enabled, we're going to do something, and if the channel is not enabled, well, we're not going to do anything else except update our status to make sure that we know that it's in fact not enabled. So here now, we quickly see examples of using the clusters and peeling elements off of them. For example, the channels comes in here, and down in this spot here, we pull off more elements of the channel of the controls, one of which is used to determine the actual data tag name of the Sartorius variable that we're going to be changing for the pump. And then this feed table location, this is going to tell us where to read our feed tables from. Another interesting thing here is that I forgot to mention before, and I should have, is this little guy here called a shift register. The reason that we put a constant here is that what we're looking to do here is we're looking to basically feed back the status of each channel every time that the loop executes. And so what happens here is things are going to happen. We're going to do some control logic, and on the end, out will come the per channel data here. It'll be aggregated into an array. It'll be sent to both the front panel so that we can see it, and it's sent to this shift register. What the shift register does essentially is store it for next time. And what happens is this is writing the shift register, and over here it's reading the shift register. So what happens is the first time through the execution loop, the while loop or the timed loop, we have a constant that basically has everything at its default value, which is zeros and disabled. This is used for only the first iteration. Afterwards, whatever we calculate replaces it. And so this way we have a running, we're working off of our most current status. Now, if we're enabled, this is true, and we are now executing inside here. The other thing we've got to look at is obviously we go back into yet another case statement. This case statement's a little bit more complex in that it's doing something reasonable in both true and false cases. What's happening here is that if our status is false and we got enabled, it means that this is the first iteration of the loop when we've actually have an enabled channel. This is an initialization logic here. And so what will happen is this is executed once upon initializing. Over here now, where we are writing our status, we throw a true into the enable, so the next time through we transition to run mode. One of the interesting things to note here is that notice that we're actually reading our status when we come in and then rewriting it later. And of course, this has to do with the convention of left to right execution. So LabVIEW is going to assume that we start here and basically follow through this execution path of various wires. So this executes first for the read, and this executes later for the write. There are a few other things I want to go over, and the timed loop, which we already touched upon, has some elements that are basically part of it. And then what I'm pointing at right now is a loop condition. The idea here is this loop will run forever unless we stop it. And what we've done here is we've attached a switch to the loop condition, and so we can then, once this becomes true, push the stop button, the program stops executing. There's another interesting thing over here. This is an iteration control, and well, it's actually iteration indicator. And what happens is when you have a loop of any sort, LabVIEW will normally have a loop iteration indicator as part of it. And what this does is it tells you the current count of the iteration. For example, If we had if we have a loop that's executing 4 times, this will the number will be 0, 1, 2, 3. There's another one that goes with the timed loop, and obviously we're not using this, and this will count up to quite large values. But if you ever need to know how many iterations have passed, well, this is a good counter. Now I will also go through various functional blocks here, and what happens is that these are graphical representations that come with LabVIEW of various logic functions. And once again, you get these off pull-down menus and you connect them together to do the kind of logic you want. And once again, the context help is really useful because it can show you what the things are, and it gives a short description of the function of the item. Now, LabVIEW also has a pretty nice overall detailed help. And so if you can't quite, if it doesn't give the context help doesn't give you quite enough information, you can click on detailed help, and within a few seconds up will come a full description of the function, and also will generally include, well, this one doesn't, but they generally include examples of how one would use this in a program. So you can pull up another VI and look at how NI at least expects you to use it. Now the last thing I'll talk about here are these little green boxes here. And notice they actually have context help, interestingly enough. These are actual sub-VIs, meaning they're VIs that we have written ourselves. It turns out that LabVIEW works on a subroutine model where every VI can either be a top-level or a standalone program, or it can be called as part of a larger program. In this case, we have 2 types of sub-VIs we're calling. This one here actually reads the CSV file, the spreadsheet file, and pulls out information based on column name. And this guy down here actually this actually calls a system routine that enables the actual communication with the Sartorius software, which of course is the one that's directly controlling the pump. So at this point, we've gone over all the data structures and programmatic items that we need to understand how the program works. So I'll stop here, and then we'll have another VI that will where we'll go over the detailed logic of how this works.